Hello, my name is Alexander Moreira with AlphaStar Academy, and today we're going to be discussing 2D conveyor belts. So in this problem, we are given conveyor belts to add to a factory floor, and after adding each conveyor belt, our goal is to determine the number of starting positions which do not have a path to the edge of the grid. And let's go through an example. In our example, there are 5 different characters that can appear. There can be conveyor belts that have already been assigned, and they can be L, R, U, or D. Each of those letters stand for the direction which they point. So R's always pass items to the right, L's always pass items to the left, U's always pass items up, and D's always pass items down. Question marks are unassigned conveyor belts, and these can be anything. So for example, I could replace all of the question marks with D's, and you'll immediately notice that anything that starts in this lower right triangle will immediately just get passed all the way down, and it'll plop off the edge of the grid. So all of these positions in this triangle can reach the edge of the grid. They are not the type of spots I'm looking for. What I'm looking for are spots in the grid that are stuck in an infinite loop or somehow blocked from reaching the edge of the grid. And for an example of such elements, let's take a look at these 3 elements. So these 2 conveyor belts, they're pointing at each other, right? We've got one conveyor belt pointing to the right, the other pointing to the left, and they're just going to pass items back and forth indefinitely. If I end up on these 2 conveyor belts, I'm never going to go anywhere other than these 2 conveyor belts. Similarly, this conveyor belt points upward onto these 2 conveyor belts. So if I start an item on this conveyor belt, it's going to go upward and then going to get stuck in this infinite loop. So these 3 conveyor belts cannot be reached, or from these 3 conveyor belts, you cannot reach the edge of the grid. You get stuck, and this is the exact thing that I want to count. The one thing that you should keep in mind in this problem is that you can also create sort of a network of conveyor belts that prevent you from ever going into some central area, right? So this is a completed loop of conveyor belts. No matter what this is, if it's down, it's going to get stuck in an infinite loop. If it's up, it's going to get stuck in an infinite loop. If it's right, going to get stuck in an infinite loop. So no matter what I assign to this central value, it's going to get pushed onto the edge here, and it's going to get stuck in this infinite loop right here. So just to chart that out, if I go up, I'm immediately stuck there. If I go to the left, I go then up and I'm stuck in my infinite loop. If I go to the right, then I am going down, then I land on this conveyor belt to the left, I go left again, then I go up, go all the way up to the top here, and I get stuck in the infinite loop. And if I start by going down, I end up on this conveyor belt, and we already saw that that ends up back at this infinite loop. So despite this being a question mark, it too is prevented from reaching the edge of the grid. So that's just one thing to keep in mind as we're solving this problem. Our first idea in this problem is to pad the grid and then apply a flood fill algorithm starting from the top left corner. So if I replace this question mark with a dot, I'm going to want to check what elements can be reached from this dot. And there are 2 things that we want to mark off. Question marks adjacent to dots can always become dots, and conveyor belts that point to dots can become dots. This means that there's some path from that conveyor belt to a dot that can reach the edge of the grid, and therefore there's some path from that conveyor belt to the edge of the grid. So let's try to do this manually. We're going to start our dot in the top left corner. Our count is 1. We're going to spread to the adjacent elements, and now our count is 3. Continuing from this element, we're going to look again at the neighboring elements. We can see there's a question mark right there, so our count is 4, and there's a conveyor belt right below. However, I can't mark off this conveyor belt because it does not point to a dot, and therefore it's not currently accessible. It may become accessible later in the future, I don't know, but right now it's not. So then we're going to continue on. We've got another question mark there. Our count's 5. We're going to spread from this dot. We're going to expand here. Our count is now 7. We're going to expand from both of those dots, and we're going to speed this up a little bit. So our count's now 9. We're going to expand there. Count's now 10. We're going to expand from this dot, so we're going to replace those two. Our count is now 12. And now something interesting happens with this dot. So it expands to these two question marks as we expect. So our count is now 14. And then it also expands to this conveyor belt. The reason why is this conveyor belt points at the dot, right? It's a downward facing conveyor belt. And we can see that below that conveyor belt is a dot. So this also gets expanded to. And then the rest of these question marks are going to get filled in as well. So we get 3 more conveyor belts there. So our count is 18. We get 3 more conveyor belts there. So our count is 21. And we get 3 more conveyor belts right there. So our count is 22. And what you can see is we've counted all of the places that are reachable from the top left corner, and therefore, to calculate the number of places that aren't reachable, we are going to simply subtract that from the total size of the grid, which is 25. So our output then would be 25 minus 22 is 3, which is exactly what we calculated by hand when we were solving this example earlier. We can now repeat this process every single time we add a conveyor belt to the grid. So before we've added anything, we can flood fill the entire thing, and we see that every region is accessible. Once we add a single conveyor belt, say one pointing to the right, we can then flood fill again, and once again, all regions are accessible. We can add a second conveyor belt, and now we've got 2 inaccessible regions. So we flood fill, we can't step onto either of these conveyor belts, so those regions are inaccessible. Great. Now we're going to add another conveyor belt, and we're going to flood fill again. Now we've got 3 regions. And continuing on, maybe say we've added 7 conveyor belts, we can flood fill again. These 2 conveyor belts are reachable because this is going to turn into a dot, which allows this to turn into a dot, which allows this to turn into a dot. But these other conveyor belts are not reachable, so we've got 5 inaccessible regions. And then adding an 8th conveyor belt, you'll notice that all of the conveyor belts are blocked off, so we end up with 9 inaccessible regions, the 8 conveyor belts and the 1 element trapped in their middle. And if you implement this, you will receive partial credit. The reason you're getting partial credit here is this is a very large grid, and repeatedly doing this flood fill over the grid Q times ends up with a runtime of Q times n squared in the worst case. So this is going to be a little bit too slow. What we can notice throughout this process is that the accessible region is always shrinking, which means that we have to restart our process or our flood fill algorithm over each time to see how much it shrank by. What would be nice is if the accessible region was always growing. That way we could use our previous progress on the flood fill algorithm to speed up our approach. We wouldn't have to recompute the accessible areas. It would always be growing. And as the problem is set up right now, that's not true. But if we consider the process in reverse, then you'll notice that the accessible region, i.e. the number of dots, is always increasing, right? Here we have fewer dots than here, which has fewer dots than here, which has fewer dots than here, and so on. So maybe if we consider this process in reverse, we won't have to use as much resources to compute our flood fill algorithm. Maybe we can use some of our previous calculations over again. So let's consider the process in reverse. We're going to start by adding all of the conveyor belts, and then we're going to flood fill the entire grid to see which places can be reached in the worst case scenario, right? The most conveyor belts have been added. From here, we'll remove conveyor belts one at a time to see how our accessible region expands. So we flood fill from 0, 0, and we see that there are 16 accessible regions and 9 inaccessible regions, the sort of elements in this square. If we remove the last conveyor belt added, which was this down conveyor belt right here, we can flood fill from the coordinates 2, 3, and we're going to expand the accessible region by 4 spots. We're going to expand from this to here. We're going to expand from this to here, and we're going to expand from this to here. So we can see that the accessible region has expanded 4 spots. And note, in order to do this expansion, I did not need to restart my flood fill. I only needed to look at these 4 additional spots. So I didn't have to loop over the entire grid again. So if I continue on, the next conveyor belt that I would have removed has already been removed by the previous step. So I just continue on to the next one. And again, the third to last conveyor belt was also already removed by prior steps. So the next conveyor belt that's interesting to remove is the fourth to last conveyor belt, which is this U. So then I'm going to start my flood fill algorithm from the coordinates of that U, and I can see that now there are only 4 regions that are inaccessible. And then I could continue on. So if I was after removing the fifth to last conveyor, that would be this L. So I would want to flood fill from the coordinates of that L, and that is going to be coordinates 1, 3, and I'm going to wind up with 3 inaccessible regions. And you can see that the accessible region is just constantly expanding. I don't have to recompute the accessible region. It's always growing and growing and growing. So by considering the process in reverse, I can improve my algorithm to a runtime of n squared plus q, rather than the algorithm we had before, which was runtime n squared times q, because for every single query, I had to loop over the entire grid again. But this process only loops over the grid a single time. It just breaks it down into multiple different steps. So let's try coding it up. All right, we're now ready to begin coding our algorithm. So the first step that we're going to want to accomplish is to fill in the grid with all of the conveyor belts. But before we can do that, we need to first fill in the entire grid with question marks. So we're going to loop over every coordinate between 0 and n plus 1 and set that coordinate to be a question mark. And now we're ready to start placing the conveyor belts on our grid. So we're going to loop over the Q conveyor belts. We're going to read in the direction the conveyor belt is facing and its coordinates. We're saving the coordinates into an array so that we can use them in the future when we go to then remove these conveyor belts at a later step in our code. And then finally, we set the grid at the coordinates of the conveyor belt equal to the character representing its direction. We are now ready to move on to step 2, which is to flood fill the entire grid starting from the coordinates 0, 0. So we're going to want to flood fill everything we can without removing any conveyor belts. So to do this, we're going to implement two separate functions. We are going to implement an update function, which keeps track of the number of spots that are accessible to us, and it's going to update our grid. And then we're going to have our flood fill call. So for the update function, we're going to have a global variable count. Every time we set a new spot on the grid equal to a dot, we're going to increase count by 1. And then we'll update the grid. Now, once we have this update function, this is going to be helpful for writing our flood fill algorithm. So flood fill, we're going to start off by first checking what character is currently at the coordinates of our grid. So we're trying to check the coordinates x, y. If the character is already a dot, this is our base case. We're going to exit our flood fill, and this is going to end the algorithm for this branch. Otherwise, we want to check, is it a question mark? Is it a letter? And can I fill it in? So if it's a question mark, then I'm always able to fill it in, right? There's no constraints on being able to fill in a question mark next to a dot. So I'll update that to be a dot, and I'll proceed on with my flood fill. Otherwise, if it is a letter, then I can only fill it in from certain directions. In particular, if the letter is currently a U, so this is a conveyor belt facing the upward direction, I can only fill in this conveyor belt if the element directly above it is a dot, right? So I would only be able to say fill in this conveyor belt if the element above it is a dot, which it's not, so I'm not able to flood fill onto this location. And the same holds true for the other characters. So if I'm looking at the character down, then the element directly below has to be a dot. Otherwise, I'm not allowed to update this position on the grid. Same for left. The element to the left has to be a dot. Same for right. The element to the right has to be a dot. And if none of these happen, right, so if it's not a question mark and it's not one of these valid letters, then I also want to terminate my flood fill algorithm. So I wasn't able to make any progress, so I'm just going to exit. However, if I did make some progress, then I want to branch out to all of the neighboring elements and check, can I fill those in too? So if my flood fill algorithm was currently here, I'd want to check these two elements to check, can I flood fill those as well? So there are 4 possibilities. If x isn't too small, I'm going to check the element to the left. If x isn't too large, I'm going to, or sorry, if x isn't too small, I'm going to check the element above. If x isn't too large, I'm going to check the element below. If y isn't too small, I'll check the element to the left. If y isn't too large, I'll check the element to the right. Now, again, the reason, just as a reminder, why we're using a n by 2, or sorry, n plus 2 by n plus 2 grid is so that the flood fill algorithm can, on its first pass, completely surround the grid. And this will allow us to detect sort of any conveyor belts on the edges that are facing outward. So for example, if this was a conveyor belt facing outward, from 0, 0, I might not be able to detect this conveyor belt facing outward. However, I am able to detect it when I flood fill all the way around the edges. I get to this point and I'll be able to work my way in through there. Once we've done this, all we have to do is flood fill at 0, 0, and this completes step 2. We're now ready for our third and final step. So we're going to deconstruct the conveyor belts in reverse. So we're going to store all of the outputs in a vector, and then at the end we'll loop over that vector and print it out in forward order. So right now we're looping over in backward order because we want to deconstruct the last conveyor belt, then the second to last conveyor belt, and so on. While we're doing this, we're going to store a variable total. This is just the total number of spots on our n+2 by n+2 grid. So if I take total and I subtract from it count, that's going to give me the number of spots that are not reachable. So this is the total number of spots. This is the total number of spots that can reach 0, 0. So the difference between them is the number of spots that cannot reach 0, which is exactly the output that we're looking for. Then we're going to use our arrays from before to recall the values of Ri and Ci, and this gives us the coordinate of the conveyor belt that we are trying to remove. And we are going to first check, has it already been removed? If it's already been removed, I can ignore it and I can proceed on to the next conveyor belt. This could happen in, say, a flood fill step that opens up a region and then sort of works backward through the conveyor belts, deleting an entire chain of conveyor belts. So here we can see on this step, we actually ended up removing 3 different conveyor belts. So if a conveyor belt's already removed, we don't want to try to remove it again. And then if it hasn't been removed, we're going to set it to a question mark to represent that it's been deleted. And then we want to perform flood fill starting at the coordinates RC. However, there's a very tricky bug that's easy to forget here. If we just apply flood fill, it may be the case that this question mark is not accessible from an area that has already been flood filled, right? So if this is at like the center of a plate of a group of conveyor belts that's been blocked off, we shouldn't start flood fill here because it can't reach the coordinate 0, 0. It's still blocked off. So we only want to begin flood fill if this question mark is adjacent to a value that's already become a dot. So to do that, we can just have 4 separate conditions and check, is the neighbor is the upward neighbor a dot, is the leftward neighbor a dot, is the downward neighbor a dot, is the rightward neighbor a dot. So we can do this here, maybe a little bit sloppy, but it works. So if the element to the left is a dot, flood fill. If the element to the right is a dot, flood fill. If the element to the top is a dot, flood fill. If the element below is a dot, flood fill. And this basically completes our algorithm here. All that's left is to, of course, print out the output, cap off our main function, and we are done. So I'm just going to give a quick scroll through the code here so that you can pause at different points in the video. So here's our main function, and here's the top portion of the code. Thank you guys so much for watching the video, and I hope you guys have an absolutely fantastic day.